The question here is, could you go over the derivation of the stress equation for pressurized, thin-walled cylinders and spheres? Let's start with thin-walled cylinders, and I have some pictures here to help us understand the mechanics. We will consider a cylinder that is capped at the ends like this one over here, so that it can be pressurized. But we will be interested only in the stresses in the cylindrical part. In that case, it turns out that the shape of the cap itself is immaterial. An example of a cylinder like this would be an air compressor. If I were to cut the cylinder in half along its axis, this will be one half, right? The picture shows how the cylinder is internally pressurized. Let's say the pressure on the inside of the cylinder is little p. Here are views of two separate cutouts of the cylinder showing internal stresses on the walls of the cylinder. This picture shows the internal normal stress on the wall in the hoop direction, and this picture shows the internal normal stress in the axial direction. Now let's call this a sigma 1 and this a sigma 2. It's very easy to see that due to symmetry, there's not going to be any shear stresses on these planes. For example, if I were to take the cylinder and twist it or something like that, there could be a shear stress on the plane here, right? But that we are not doing that, right? And therefore, there is no shear stress in that direction. Similarly, if we were to take the cylinder and shear it like this, for example, right, there would be a shear stress on that plane, but that's not being done either. And therefore, only kind of stress that we will have on the walls of the cylinder would be principal stresses, sigma 1 in the hoop direction and sigma 2 in the axial direction. And these stress components are shown on a three-dimensional element taken out at this point over here. Now let's go ahead and define the coordinate system that we want to use here in our analysis. The problem here is a good candidate for the use of the cylindrical coordinate system because the geometry is a cylinder and the loading is also cylindrical. For example, the pressure here is acting in the radial direction, right? So using the cylindrical coordinate system, let's call the radial direction as r, hoop direction as theta, and the axial direction as z. The outer surface of the cylinder is a free surface and therefore there are no stresses on that. In other words, there are no stresses on this plane, which is the plane perpendicular to the r-axis. The pressure P is acting on the underside of this three-dimensional element. Therefore, there's going to be a principal stress in the direction r on that surface, and the magnitude of that is going to be exactly equal to P. So how do sigma 1 and sigma 2 relate to P? Well, let's go ahead and derive equations for them. Earlier I said the shape of the cap itself is immaterial, right? Now why did I say that? In order to answer a question like that, let's first derive a useful sight result. Supposing, say, I have a 2D Cartesian coordinate system, xy system, and I have a little planar differential element from A to B. This differential element is subjected to a pressure P, and I'm interested in finding the component of the force due to this pressure P on this little planar differential element in the x direction. So here's my analysis. dFx, which is the force due to the pressure in the x direction, equals P times dl, which is the force due to the pressure on the plate, and this force is acting in that direction, right? So I am interested in the horizontal component, and therefore I need to multiply that by sine theta in order to resolve that force in that direction. So in the second line here, I'm grouping dl and sine theta together because now we come back and look at this little geometry here. We see that dl sine theta is simply dy, right? And therefore what we have is dfx equals simply p times dy. And you see that the angle theta has disappeared completely. So the force in the x direction depends only on the projection of AB in the y direction. Suppose I have two differential elements, AB and AC, both of which are subjected to the same pressure P. Both differential elements have the same projection in the y direction, dy. So according to the results we just derived, the force on AB in the x direction is exactly equal to the force on AC in the same direction, x direction. Now referring back to the cylinder with caps, if I'm interested in finding the force on one of the caps in the direction of the axis of the cylinder, right, that force is simply going to be equal to pressure multiplied by the projection of the surface of the cap in the direction perpendicular to the axis of the cylinder. Therefore, the shape of the cap itself is immaterial. Now combining the results we just derived and Newton's law, specifically the force equilibrium equation, it's very easy for us to derive an equation for sigma 1 and an equation for sigma 2. So that's what I'm doing here on this slide. On the left, we are deriving an equation for sigma 1. On the right, we are deriving an equation for sigma 2. You saw these cutouts on the earlier slide, right? So I have just completed the free body diagram for these cutouts. In each case, there's an internal pressure P acting on the inner surface of the cutouts. Now let's consider these one at a time, starting with the one on the left side. Now I'm going to define the x-axis to be perpendicular to this plane right here. We're going to sum up the forces in the x direction. The stress sigma 1 is acting only on the walls of the cylinder. So on this free body diagram, there are two planes where they are acting. So what I'm doing here is I'm finding the force on one of them and multiplying that by 2. Force on one of them would be sigma 1 multiplied by this area right here, right? That will be L multiplied by little t. L multiplied by little t. That's what you see here. The force due to the internal pressure P in the direction x, on the basis of the results we derived in the earlier slide, would be simply P multiplied by this area right here. That is the projection of this cylindrical part in the direction perpendicular to the x-axis. And that area is L multiplied by 2R. That's it. So those are the two forces acting on this free body diagram, and therefore sum of them in the x direction must be equal to 0. And that gives us this expression for sigma 1. Sigma 1 equals P times R over T. Following the same approach, we derive an expression for sigma 2 over here on the right column. I'm defining the x-axis to be perpendicular to this plane right there. The force due to sigma 2 in the x direction would be sigma 2 multiplied by the area of the walls as you go around the circumference there. That will be 2 pi r multiplied by little t. The force due to P in the x direction, again utilizing the results we derived in the earlier slide, would simply be equal to P multiplied by the projected area of this curved part onto a plane perpendicular to the x-axis. That will be pi r squared. And this leads to this expression for sigma 2. So sigma 2 is P times R over 2T. So you can see sigma 1 is twice as large as sigma 2. Now that we have covered all the fundamentals, deriving an equation for the stresses on the walls of a thin-walled sphere is fairly straightforward. So here's a spherical tank subjected to an internal pressure P, and here we see a cutout of that, and this cutout was obtained by cutting the sphere in half. In other words, this is a semi-spherical part of the sphere. Denoting the normal stress on the wall as sigma, and here is my equilibrium equation written in the x direction. So x direction is taken to be perpendicular to this plane right there. And this leads to this expression for sigma. Sigma equal P times R over 2T. And here are the stresses acting on a three-dimensional element, differential element, taken out at this point right there. And you can see, due to symmetry, this normal stress and this normal stress are equal to each other. And is given by this expression.